All right, let's get right into it. We all want to make smart decisions, right? Decisions based on actual data, not just a gut feeling. But how do we really do that? Well, today we're going to break down the powerful and you'll see surprisingly controversial tool that companies use to figure out what we, the users, actually want. So picture this. You run a website, you launch some slick new feature. Maybe you just change the color of a button, and suddenly sales go up. That's awesome. But then that little voice in the back of your head starts asking, wait, was that my brilliant change? Or did I just get lucky that day? How can you possibly know for sure? Let's use a simpler example. Imagine you own a salon. You pour a ton of time and money into a gorgeous new homepage. The photos are amazing, the testimonials are perfect, but looking good is one thing. The whole point is to get more people booking appointments. How do you prove, actually prove, that the new design is the reason for more business? You can't just guess. And that really sets the stage here. It's a classic story, a tale of two websites, the one you have now and the new one you really hope is better. And luckily for us, there's a specific method designed to figure out which version gets the happy ending. That method is called A/B testing. You might also hear it called split testing, and the concept, it's actually beautiful in its simplicity. You take your original page, that's version A, your control, and you create a new version, B, your variation. Then you show version A to one group of people and version B to a totally separate but similar group of people all at the same time. Then you just see which one wins. No more guesswork. So how do you actually run one of these things? I mean, it's not just about whipping up a new design and seeing what happens. There's a proper way to do it, a playbook, to make sure the results you get are actually meaningful. And here's that playbook, boiled down to its basics. It's really just 4 key steps. First, you need a hypothesis, an educated guess. Then you create your different versions. Step 3, you run the test, making sure you get enough data. And finally, the most important part, you analyze the results. Now that first step, the hypothesis, is absolutely critical. A vague goal like, let's make the page better, it's useless for testing. A good hypothesis isolates one specific change and predicts a specific outcome. Something just like this. If I change the call us button from blue to orange, I believe more users will click on it. Now that is something you can actually test. So you do it. You run your test with the new orange button and boom, the results are in. The new version gets 5% more clicks. This feels like a huge win, right? Time to pop the champagne and make the button orange for everybody. But not so fast. This is where it starts to get tricky. How do we know that 5% increase is legit? With any group of people, there's just random chance. Maybe the people who happened to see the orange button were just in a clicky mood that day. How do we separate a real improvement, what we call the signal, from all that random noise? To answer that question, we have to step out of the world of design and into the world of math. We need a special tool that can help us figure out if our result is the real deal. And that brings us to this big idea, statistical significance. At its core, statistical significance is just a formal way of asking, what are the odds that this result is a total fluke? If the probability that your result happened by pure random luck is low enough, then you can be a lot more confident that your change actually caused that result. So how does this actually work? Well, statisticians start out by playing devil's advocate. They begin with an assumption called the null hypothesis, which is the idea that your change did absolutely nothing, zero effect. Then they calculate something called a p-value. That's the probability of seeing the results you got, assuming your change actually did nothing. And the classic rule of thumb is, if that p-value is 5% or less, you get to reject that devil's advocate idea and declare your result statistically significant. But that simple rule, that p-value of 0.05, that's where things get really messy. Because in the real world of high-stakes testing at places like, Google or Apple, the experts have some pretty serious warnings about getting this stuff wrong. And this quote from a few researchers at Apple really hammers the point home. If you don't run your test on enough people, if your sample size is too small, your entire experiment can be totally worthless. You could have a genuinely game-changing idea, but the test just won't be powerful enough to see it. And that leads to, in their words, misinformed and costly decisions. The stakes are incredibly high. And the details don't stop there. The experts also point out you have to be super precise about what kind of lift or improvement you're even looking for. Are you talking about an absolute lift, like going from a 10% conversion rate to 12%? Or are you talking about a relative lift, which would be a 20% increase? It seems like a small detail, but it can completely change how you set up your test. Okay, so take a look at this. It might seem complicated, but it shows a really smart technique the pros use. Before a test even starts, they can calculate what's called a minimum observed difference. That's that dashed gray line. Think of it like the finish line. A result has to cross that line to be taken seriously. You can see how the blue bars, the significant results, are mostly to the right of that line, while the orange ones aren't. It's a way of defining what success looks like before you even begin. And here's another huge trap they warn about. Let's say one person comes to your site 5 different times. If you count that as 5 separate data points from 5 different people, you are making a massive mistake. Those visits aren't independent. They're all from the same person. That's correlated data. And if you don't account for it, you can get a result that looks amazing, but is actually complete garbage. You know, all these expert warnings, all these little details, they're actually pointing to a much, much bigger issue. The entire concept of calling a result significant or not significant is now at the heart of a huge debate in the entire scientific world. See, this idea isn't some ancient law of the universe. It was really popularized back in 1925 when a statistician named Ronald Fisher just suggested that 1 in 20 odds that 0.05 p-value was a convenient cutoff. But what started as a simple convenience has spiraled into a bit of a crisis. Fast forward to 2016, and the American Statistical Association itself is issuing warnings about its misuse. And by 2019, you have over 800 scientists demanding we abandon the term completely. And this quote, this is the bombshell. The main professional group for statisticians in the US flat out said it's time to stop. Not just the phrase, but anything like it. Significantly different, the little p less than 0.05 you see in studies, all of it. They're saying the whole framework needs to go. So what's the deal? Why the big rebellion? Well, there are a few huge reasons. First, statistically significant does not mean important in the real world. A tiny, totally useless improvement can be statistically significant if you have enough data, but who cares? Second, it leads to bad science, what some call a crisis of unreplicable research, where other scientists can't get the same results. And finally, it creates this false black and white world. Either an effect is real or it isn't. But reality is a spectrum. The real question shouldn't just be, is there an effect? It should be, how big is the effect? Which, of course, leaves us with this massive question. A/B testing is an incredible tool for trying out new ideas. But if the very standard we've used for a century to judge those ideas is broken, then what do we do? The conversation is now shifting away from a simple yes or no and toward focusing on the size of the improvement and our level of certainty. The real challenge now for everyone is figuring out how to make smart decisions when the line between a real breakthrough and just random noise is a whole lot fuzzier than we thought.